Hello and welcome to lecture 28 of the course Computational Complexity. In the previous lecture, we motivated randomized algorithms and we defined the complexity class RP, which stands for Randomized Polynomial Time, which is a complexity class used to describe computational problems or languages that have a one-sided polynomial time algorithm with one-sided error. So the one-sided error being false negatives, right? So whenever there is an X that is in the language, it may report that the algorithm may report that X is not in the language, but not the other way around, right? So today we will see in this lecture we will see two more complexity classes, or perhaps three more. One starting with co-RP, right? So co-RP, just like we have seen co-NP and co-NL, stands for all the languages that are complement of the languages that are found in RP, right? So the first definition is along the same lines. L is in co-RP if L complement is in RP. Right? So if and only if L complement is in RP, right? So another way to define it is, which is equivalent, you will see why they are equivalent, is that L is in co-RP if there is a probabilistic polynomial time machine, right? Probabilistic machine which runs in polynomial time such that whenever X is in the language, it accepts with probability 1, and whenever X is not in the language, it accepts with probability at most half, right? So maybe over here we have the grid picture for RP. So now let me draw the similar grid for co-RP. So here it is algorithm outputs yes, algorithm outputs no, X is in the language and X is not in the language. Whenever X is in the language, it will accept always. Whenever X is not in the language, it may accept, but it could also, of course it can reject, but it may also accept. However, this zone, we never get into this zone, meaning so there is no false positive, or sorry, there is no false there's only false positive. An X that is not in the language may be incorrectly reported as being in the language, but not the other way around. So in the case of RP, we had only false negatives, but in the case of co-RP, we have false positives. Right? So this is the description of co-RP. Let us see why this definition is the same as the previous definition. Okay. Suppose there is an X. So consider this. So consider an L which has this description. This meaning the description over here. Maybe I'll just, for the co-RP machine, we'll show why the complement of that language L has to be in RP. Okay. Suppose X is in L. Okay. Suppose X is in L, then we can say that X is not in L complement, right? That is the same thing. And if X is not in L complement, so I'll erase this circle. If X is not in L complement, X is in L. In that case, the probability of Mx accepting is with probability 1, right? So now think of a machine M bar, okay? So M bar just flips the output of M, okay? Flips output of M, okay? So if X is in the language, then the probability of M accepting is 1, so the probability of M bar accepting is 0, because M bar is just going to say the opposite of whatever M is saying. And whenever X is not in the language, the probability of M bar accepting is at least half, because all the yeses becomes accepts become rejects and the rejects become accepts. So the probability of M accepting was at most half, the probability of M bar accepting was at least half. But then X is not in L means that X is in L complement, right? So now when we view these two statements, the ones that are written in blue, as statements of with respect to L complement and the machine M bar, we see that M bar is an RP decider for L complement, right? So whenever X is in L complement, M bar accepts with probability at least half, which is the RP definition, and whenever X is not in L complement, M bar accepts with probability 0, right? So which is again the RP definition. So hence we can conclude that L is in RP. So we started with, sorry, L complement is in RP. We started with L being in co-RP, and we are able to infer that L complement is in RP. So it's if and only if. And similarly, you can make the other direction inference as well. So this is what we saw now is one direction inference. L is in co-RP implies L complement is in RP, but the other direction is also not difficult to see. Basically, whatever we just saw, you can make the exact same arguments in the reverse direction. Again, some very quick points. There could be false positives in a co-RP machine, but no false negatives. And just like we could replace the half in the RP with an arbitrary quantity, just like that, this half here, the half over here, this half also can be replaced with an. So this shows it the acceptance for X naught in the language should be at most half, but then this could be instead of this half we could have at most 2/3 or 3/4 or 0.9. And we can even come very close to 1. We could come polynomially close to 1, like it could be 1 minus 1 over n power k, but we cannot come closer than 1 minus inverse polynomial. This is what, and still if you have 1 minus 1 by n over k, it could still be boosted and the probability of error can be reduced. So 1 minus 1 over n over k, this means that the probability of error is, whenever X is not in the language, this is the probability of error, right? So, but even this 1 minus inverse polynomial error can be brought down with polynomial many repeats. Okay. Right. So again, the way the repeats work, etc., it's very similar, and I believe this notes has some. I've formally written down this point, but we can go through it when I share the notes. I will just explain one more example, but in fact this is also a co-RP example, RP example, but this is another problem. So this problem is called polynomial identity testing. Okay. So it may sound very simple, but it happens to be a very fundamental problem, which is very interesting, especially in terms of in the perspective of randomized algorithms, right? The problem is a given polynomial identically 0? So what do I mean by identically 0? So consider this x square minus 2x plus 1, right? This polynomial can be set to 0, let's say when x is equal to 1, right? This polynomial evaluates to 0, right? This evaluates to 0, but this is not always 0. When x is equal to 3, for instance, you get 9 minus 6 plus 1, which is equal to 4, right? So this polynomial is not identically 0. Sorry, there is some issue. It is not identically 0. Okay. However, maybe to give an example of another polynomial that is identically 0 could be, these are the polynomials that are always 0. Maybe so x squared minus something like this, right? X squared minus 4x plus 4 minus x minus 2 squared. So if you expand the second term, x minus 2 squared, you will get exactly the same expression that is the first term, and so they will cancel out. So this is identically 0. So it should always be equal to 0 no matter what value you assign to x. That is what identically 0 means. So for instance, I'm here in the main text, there is this polynomial f of x. So is f of x identically 0? Well, so it's written as a difference. So both the terms, the leading monomial is x cubed, right? So here if we multiply these three things, x minus 1, x plus 3 and x minus 6, we get x cubed. The constant term of the left hand side, or the first term, is minus 1 into plus 3 into minus 6, so it is plus 18. Here also it's plus 18. But if you look closely, for instance, if you look at the x squared coefficient, so x squared coefficient is just the sum of the three constants. So it is 3 minus 1 minus 6, which is actually minus 4. So the coefficient of x squared is incorrect. So we understand that this is actually not identically 0, but when you look at it first glance, it's not very clear, right? So this is the problem, polynomial identity testing. So how do we? So let us try for a simple algorithm, simple randomized algorithm that can be used to decide this problem. So one approach is take the polynomial, and you just substitute some value. Let's say x is equal to 5, and then see what this polynomial evaluates to, right? If it evaluates to 0, then you say it is 0 polynomial. If it evaluates to non-zero, it says it's non-zero polynomial. So let's see what is the success rate and what is the failure rate, right? So let's take the earlier example, x square minus 2x plus 1. So if you happen to evaluate this at x is equal to 1, you will get 0, and then you will report that this is the 0 polynomial. However, if you evaluate it at x is equal to 2, for instance, you will evaluate the evaluation. So x is equal to 1, so let's say this is px, right? P of 1 is 0, whereas P of 2 is 1. So if you evaluate it at x is equal to x is equal to 1, you get 0, and if this is the random point at which you decide to evaluate, the algorithm will report it is 0. It is 0 polynomial, whereas the algorithm will report not 0 polynomial, right? So here there are actually, so I said wrong. I earlier said this is a RP, it has an RP algorithm, but this is a co-RP algorithm, right? Because the polynomial could be not the 0 polynomial, but there are false positives, right? We may incorrectly state that a non-zero polynomial is a 0 polynomial, right? So here it is certainly not a 0 polynomial, but we are reporting it as a 0 polynomial. So this is a false positives are there, but notice that we will never have false negatives. This is because false negatives mean we incorrectly report something as not a 0 polynomial when it is a 0 polynomial. But when the actual polynomial is a 0 polynomial, no matter what you substitute it into, you will get the evaluation to be 0. So this is right. So this is we can get false net positives, but not false negatives. So this is a co-RP algorithm. It's a polynomial time algorithm. You evaluate the polynomial at a certain value, right? However, so this seems very simple algorithm, but this is I said that this is a fundamental important problem. This is a problem for which, in the case of single variable, so all these polynomials we considered have only one variable x. But when we have multiple variables, right, the multivariate case of this problem, there is no efficient way of deciding whether a given polynomial is a zero polynomial or not in deterministic time. But in the case of randomized algorithm, we have this algorithm that I just described. Whatever I just described here, you could also describe, you could also generalize to multivariate case. So you just pick x is equal to something and y equal to something, right? All of this you can do, right? But there is no known deterministic algorithm. So this is a candidate problem that makes one think that randomness does indeed gives more power as compared to deterministic polynomial time algorithms. So this is a co-RP algorithm, right? So let me just describe this boosting as an exercise. So what I have stated here is that if we have an algorithm, again this is stated in the RP setting. If we have an algorithm for which the probability of acceptance is 1 by px, so where px is a polynomial, so it's inverse polynomial, and probability that x not in L is accepted is 0, right? So this is the RP setting. Then we could, by doing enough boosting, right? So here we have inverse polynomial, something very very close to 0, 1 by px. We could boost that to something like, so something extremely close to 1. You could, by repeating, you could get 1 minus e power minus qx, where q is any polynomial. So think about how to, so there is nothing much to think about, it's rather working out. It's exactly what I described. So when you repeat it, you will have to, which answer do you say, right? So when one is a yes and one is a no, which answer do you say? This is one part that you have to think. And then what is the probability of error? Right? The probability of error is when x is in L and it is still reported as a false negative. It is reported as being not in L. So this probability will go down with repeats. So just work out how many repeats are necessary to get from 1 by px to 1 minus e power minus qx. Okay, so that is the only part that needs to be worked out, but you can work out for and convince yourself. Okay, so that concludes the small part about co-RP. Now I want to move to a two-sided error model, right? So till now we've seen RP and co-RP. Both cases we had one-sided error. RP had false negatives but no false positives. Co-RP had false positives but no false negatives. Now we are going to see BPP, which stands for bounded error probabilistic polynomial time. This is shortened as BPP. BPP, L is in BPP if there is a probabilistic polynomial time machine such that whenever x is in the language, it is accepted with probability 2/3, and whenever x is not in the language, it is accepted with probability at most 1/3. Okay. So in the case of RP, we had the first one was greater than half and second one was equal to 0. In the case of co-RP, the first one was 1 equal to 1 and the second one was less than or equal to half. So here instead, in both the cases, one of them was fixed at the desired value. But in the case of BPP, both of them, both of the errors are possible. So the false negatives are possible, false positives are also possible. However, the probability of acceptance in both the cases is different, or the bounds are different. Okay, so So the bounds are different. So the key thing here to note is that between 2/3 and 1/3 there is a gap, right? So it's not like when something is in the language, the probability of acceptance is significantly higher than when it is not in the language. So this is at least 2/3, it is at most 1/3, right? And yeah, so I'll first state this too. First thing is that RP and co-RP are contained in BPP. This is a small exercise. So again, as I said, if we had an RP machine, right, this was at least half, and this is equal to 0. If you had a co-RP machine, right, this was equal to 1 and this was at most half, right. So if you have an RP machine, then how do we get a BPP machine? So this does not fit in the BPP model because the probability of when X is in L, the probability of acceptance is only at least half. When X is not in L, the probability of acceptance is 0, which is okay because BPP requires it to be at most 1/3, and this is at most 1/3. What we can do is to repeat it twice. Okay, repeat twice. What would be the error for an RP when you repeat it 2 times? The error here is at most half, but the error will go down to 1/4 because both the trials have to be successful, or both the trials have to be incorrect. So this half will become 3/4, which is bigger than 2/3. And similarly in the case of co-RP. So just by repeating the RP algorithm 2 times, we will get the probability of success or probability of acceptance in the case of X is equal to L to be at least 3/4. And the probability of acceptance in the case of X is not equal to L remains 0, right. So again, repeat twice, and when both the trials or one of the trials accept and one of the trials is reject, then we know that there are possibility of false negatives, so we say accept, because whenever it says accept, we know it for sure it is correct, right, in the case of RP. In the case of co-RP, the decision is the opposite. Whenever you accept, only when all of them accept, right, because there are false positives. But then the same argument will take down the probability of error to 1/4. So when X is not in L, the probability that it is accepted can be upper bounded by 1/4. So you can work out this. If necessary, we could work out this in one of those meetings as well, live sessions as well. And just like we saw for RP and co-RP, where we mentioned that this half is arbitrary, even the 2/3 and 1/3 in the case of BPP are arbitrary. But let us see to what extent we can move them around, right? So one thing that you may guess is that if I make the probability of if I make both of them from 2/3, if I bring down to half, and this 1/3 is also brought up to half, then there is no distinction between X being in the language and X being not in the language, right? Both of them will accept with probability half. So then you may as well just output accept and reject with probability half without looking at the input. So that is not going to be useful, right? So we need some demarcation between X is in the language and X is not in the language. So the probability of acceptance when X is not in the language should be something above half, and the probability of acceptance when X is not in the language should be something just below half. So how much gap should we maintain between half, or between the X is in the language and X is not in the language, right? So it turns out that inverse polynomial is enough. So if we have the probability of if there is a probabilistic polynomial time machine such that whenever X is in the language, it is accepted with probability half plus inverse polynomial, and whenever x is not in the language, it is accepted with probability at most half minus inverse polynomial, right? So the only gap that we are saying is half plus inverse polynomial in the case of x is in the language, and half minus inverse polynomial, that is the upper bound, when x is not in the language. For any polynomial px, right? So in fact, it's strictly speaking, it is p size of x, right? Because x is the input and the length of the input is what we are referring to. Then L is in BPP, meaning then we can. So what this really says is that if we have L, which or if you have a machine M for L which satisfies this half plus 1 by px and half minus 1 by px, then by boosting we can get to 2/3 1/3. Let's see how we can do that. In the case of one-sided error, the boosting was easy, right? Because we only got one type of error. So when we saw when we had a guess a random assignment and say that phi is satisfiable, not satisfiable, if we had even one of the trials outputting phi is satisfiable, the trials outputted satisfiable because we found a satisfying assignment. So then we do not need to look at, we could safely ignore all the other trials that outputted phi is not satisfiable, right? However, so what I am saying is that the boosting in the case of one-sided error was relatively easy. However, in this case, both could happen. X being in the language being incorrectly reported as x being not in the language, and x being not in the language being incorrectly reported as x being in the language, false negatives as well as false positives. So we cannot afford to do this kind of decision making. If there is at least one accept, does not mean that you can accept. Same for reject. So we need to do something else. So what we will do, I will first explain what we do and then explain why we do this, right? What we do is we run the machine some number of times, let's say t number of times. We repeat it t number of times, and then we decide based on the majority. So we decide, let's say we run 100 times, and if 51 of the times it's accept, we accept, and let's say anything else you reject. And the claim is that when x is if we have even this kind of gap, right? X is in the language, half plus 1 by px, x is not in the language, the probability of acceptance is at most half minus 1 by px. Then if you repeat it many times, then it is likely that the expected number of accepts is significantly higher than expected number of rejects. So let's say this is true. X is in the language, half plus 1 by px, not in the language, half minus 1 by px. Then let's say you repeat 1000 times. Again, this is just to give a intuition. Then the probability of accepts are likely to be around, let's say, at least 505, and the probability of rejects are going to be at most 495, right? So because there is a gap, and this gap is pronounced when you repeat it. In one trial it's not pronounced, it's very close to half, but when you repeat it many times, this gap becomes pronounced. So when you repeat it, you are likely to see more than 505 accepts if x is in the language, or less than 495 rejects when x is 495 accepts when x is not in the language. So you can safely accept or reject based on this. This is the key idea for this. However, I will not go into the details of this because it's a bit technical. This is executed by something called Chernoff Bound. What is Chernoff Bound? It says that if there are n random variables x1 to xn, n01 random variables, and all of them being independent, and all of them being identically distributed with probability rho, okay, with probability rho, meaning the probability that each one of them being equal to 1 is rho. and the probability of each one of them being equal to 0 is, so they are 0 1 random variables. So the probability that xi equal to 0 is 1 minus rho, and this is true for all the i's, all the x's. Now consider x to be summation of xi, just how many of them are 1, and the expectation of x is mu, and expectation of x is nothing but n times rho, because it's for each one of them the expectation is rho, n times the expectation is, by linearity of expectations it is n times rho. And in this case Chernoff bound says that, so maybe just look at these two statements over here, these two red statements. It says that the probability that x is bigger, significantly bigger than the mean, right? So mu is the mean of expectation of x. The probability of x being significantly bigger than the expectation is e power, right, minus epsilon squared by 3 times mu, and it being significantly smaller than the expectation is also, again, not that significantly, it is e power minus epsilon squared. So the point is that this is exponential quantity. So what it actually says that if x is, this is the mean of x, okay, so suppose this is the mean of x mu, if we have done sufficiently many trials, right, many trials are done, then we are likely to see we are likely to see x being very closely concentrated around the mean. The probability of, so this is x, the distribution of x is very likely to be strongly concentrated around the mean. It is unlikely to vary significantly. The probability of x moving significantly away from mu in the positive or the negative side is very, very low. So the probability of x going far away is very small. That's what Chernoff bound says. And so when you repeat it many times, this gap of half plus 1 by px and 1 minus px becomes more and more pronounced, and the rest is just calculating this, okay, the rest is just calculating this. And so there is a machine, we call it, we repeat m t times. So again we have to evaluate what is t, what kind of t works, and this machine, this machine that or this repeated machine, let us call it m star, this accepts if at least half of the outputs are accept, otherwise it rejects, and then we can calculate the probability of error. And thanks to Chernoff bound, this probability of error is 1/4 for either case, for x being in the language and sorry, when x is not in the language, sorry, if x is in the language, what is the probability that x is not accepted, right? This comes out to be 1/4, right? So this which means that this probability, when x is in the language, it will be accepted with probability at least 3/4, and the below one, when x is not in the language, it will be accepted with probability at most 1/4, which is better than 2/3 1/3 that the BPP definition suggests, right? So this is what I want to say about BPP. Again, once again, I want to say that this 2/3 1/3 could be replaced by 3/4 1/4, or 9 by 10 1 by 10, right? Or as we saw here, it could be very close to half also, half plus some constant, half minus, not half plus constant or certainly works, but half plus 1 by polynomial also works, and half minus 1 by polynomial. So just by repeating it many times and by virtue of Chernoff bound, we can infer that even from a small gap, half plus 1 by px and half minus 1 by px, you can boost it sufficiently to get something like 2/3 1/3 or 3/4 1/4. Right? So all that you do is you repeat it many times, and whatever is the majority outcome that happens more number of times, you output that. and the rest of the so that the calculation, even though it may seem like many symbols and calculations, it's just two things. One is just applying Chernoff bound, and two, you figuring out what is the number of times that one has to repeat so that we will get a constant. So the number of times one has to repeat is rho times 2 times p square into ln4. So the number of repeats is again just polynomial. That's why it was important to have a polynomial 1 by px here. If instead of 1 by px, if we had 1 by 2 power x or something, then this would not have worked, because then in place we would have to repeat exponentially many times, right? So that is about BPP and how we can boost the probability of success in BPP. However, as I already said, BPP contains both RP and co-RP. And usually when somebody says a randomized algorithm, one tends to think of BPP because it's more general than RP and co-RP. Because RP and co-RP are restrictive in terms of the error type allowed. One of them allows only false negative, one of them only false positive, but BPP is more versatile that way, right? So, and BPP and it contains both of them, so it is easier to work with BPP assumption, right? And I will conclude this lecture by saying one point about what is called Monte Carlo and Las Vegas algorithms, right? So in any algorithm, right, these are two different. Monte Carlo and Las Vegas are two cities. One of them is in Europe. Monte Carlo is in Europe, somewhere near Italy, and Las Vegas is in USA, in the state of Nevada. Both of them are known for like very flashy lifestyle and presence of casinos, right? So people tend to gamble over there, which is why they have been associated with the class of randomized algorithms and randomized complexity classes. So in any algorithm, what do we want, right? In any deterministic algorithm, say, we want the outcome to be correct, and we want to happen efficiently in good running time, right? Two things: correct output in decent time. And in the case of randomized algorithms, because things are random, right? Meaning the setting is random, you make random choices. So we tend to relax one of these. So there are two things that we could relax. So till now what we have seen is we have been relaxing the requirement of always correct answer. This requirement we have been relaxing. How have we been relaxing this? By allowing for some error probability. We allow some error, but then we try to make the error controlled so that we can manage the probability of error. And this and the running time is fixed. So one situation is when we relax the correctness requirement but keep the running time requirement unchanged, and this is called Monte Carlo algorithm. Running time is fixed, but the probability of error we try to manage. You keep it at a fixed quantity so that you could, or you upper bound it, lower something, right? Whatever we have seen so far, right, RP, co-RP and BPP are examples of complexity classes that pertain to Monte Carlo algorithms. What we have not seen so far is Las Vegas algorithms, where we relax the running time requirement. So there the answer will always be correct, but the running time may change. So the running time may increase, decrease based on the input. So one example, even though it's not a decision problem, is quicksort. We know you may have heard of this randomized quicksort. The randomized quicksort chooses the pivot randomly, and you may have studied that even in the case of randomized quicksort, even when the pivot is randomly chosen, the running time could be as bad as n squared. The worst case running time could be as bad as n squared. However, it could perform well, and in fact in the case of randomized quicksort, most of the time it is expected to perform well, and the running time is usually number of comparisons, expected number of comparisons is n log n. So the running time varies, but the correctness is always, so at the end of it, whether you take n log n time or n squared time, the array that is given to you is sorted correctly. So the correctness is always guaranteed. This is the this is the class of Las Vegas algorithm. Running time fluctuates, but algorithm is always correct. Right? Sometimes what we do in the case of quicksort, we say expected running time is bounded. So we bound expected running time. And the complexity class that pertains to this, one complexity class that pertains to this is called ZPP. Okay, ZPP stands for zero error probabilistic polynomial time. Right, that is abbreviated as ZPP, and I think we will see this in the next lecture, and I will quickly summarize what we have seen so far. We have seen co-RP, right, which corresponds to the languages that are the complements of the languages that are the complements of the languages in RP, and we saw that it has false positives but no false negatives. Right, there also we saw the probability of success that half is an arbitrary choice, and we have some leeway there. We saw polynomial identity testing, and saw a co-RP algorithm for it, right, where we potentially can get false positives. Right, we could, even though the polynomial is not identically zero, we may incorrectly declare it as identically zero. Right, but it cannot have false negatives. Then we saw BPP, which is bounded error probabilistic polynomial time. Sorry, and this allowed for both errors. It is not one-sided; it is two-sided error. Right, so this is called two-sided error. Both false negatives and false positives it allowed. Right, where the only thing that we really need is a gap between the acceptance probability in the case when x is in L and x is not in L. Even though we write 2/3, 1/3, it could be 3/4, 1/4, or 9/10, 1/10. And we saw that the gap could be brought as close as half plus inverse polynomial and half minus inverse polynomial, just leaving a inverse polynomial gap. And this, how we can boost it? We boost it by using Chernoff bound. We repeat it many times and we take the majority outcome. And I did not get into the details of the Chernoff bound calculation, but it is rather standard in the field of randomized algorithms, and I urge you to look that up. Finally, we saw what is Monte Carlo and Las Vegas algorithms. Monte Carlo algorithms are those where running time is fixed but correctness is changes because of some errors are possible, so we bound the errors. Las Vegas algorithms are running time varies but are always correct. Right? So we bound the like expectation of running time or something like that. And all that we have seen so far, RP, co-RP, and BPP correspond to Monte Carlo algorithms. And what we are yet to see is a complexity class that corresponds to Las Vegas algorithms called ZPP, okay, which stands for zero error probabilistic polynomial time, which we will see in the next lecture.